let's look at some of those reference electrodes. The key property of a reference electrode: to serve as a reference electrode, the half cell must have a potential voltage that remains essentially constant over the course of a measurement. So you want that reference electrode's potential to be stable over time. When you guys did the lab where you were making a silver and copper cell, those concentrations were changing over time, because as the reaction progressed, you were going to deposit silver, you were going to oxidize copper, the concentration of both those species stayed the same. With that saturated KCl solution, the amount of potassium and the amount of chloride will be constant as long as there is that solid KCl in solution. Right? So we're going to use a saturated solution. In that saturated solution, dissolving and precipitating equilibria hold the concentrations constant, right? And because they've got constant ion concentrations, you've got a constant reference electrode potential. It may not be zero. In fact, it's usually not zero. The only time it's going to be zero is with the standard hydrogen reference electrode, and those are not very common. The saturated silver chloride electrode or calomel electrode is way more common to see. Right? So they're going to have a voltage that's not zero. So when we make our measurement and we want to know what the voltage is over here on this half of the cell, we need to account for the fact that we're not measuring that relative to zero most of the time. It's relative to something else. Yep. The three most important reference electrodes for potentiometry are the standard hydrogen reference electrode. That is the reference electrode. That is the final big boss of electrodes. It is also really uncommon. That's the one that says, I'm making hydrogen gas on a platinum electrode surface. My reference is zero, right? That is the zero reference. That is why reduction of hydrogen is zero on your standard reduction table. Then you've got the saturated silver chloride electrode, so that's an AgCl reference electrode. This guy is probably the most common. You then have a saturated calomel electrode. Now, your saturated calomel electrode is actually looking at silver and mercury together, so those are a lot less common these days. They do have some advantages in terms of voltage stability over the saturated silver chloride electrode. They're not as environmentally friendly, so we don't see them as often. So the one to really watch out for, and this guy over here. All these reference electrodes use a saturated solution to hold the potential of the reference electrode constant during the potentiometry measurements. The standard reference electrode for tabulated standard reductions is that hydrogen reference electrode, the SHE. The standard hydrogen reference electrode is difficult because it requires you're making H2 gas. It's also going to require that you work with 1 molar strong acid. A freshly prepared catalytic surface is needed. It's easy to get that catalytic surface messed up. It is a poison. That's the word that they use for when you get chemical contamination on the surface of your electrode. Because they're easier to use, the silver chloride electrode and the calomel reference electrode are used with much greater frequency than the SHE electrode. So here is what this AgCl reference electrode looks like, as I have drawn it, because I think it's a little easier to understand that. So all you've got is you've got a silver wire, and that silver wire is into your reference electrode. And then you have a saturated solution in here of Ag and potassium chloride, AgCl potassium chloride. You're going to build up on the surface of this electrode some AgCl solid, right? And that's going to be what's in equilibrium with the solution, right? It's this AgCl in solution where you're able to put out Ag and Cl in solution, but it's in an equilibrium process with that saturated solid at the bottom, so the concentration stays constant. Our Nernst equation says there's no change to our concentration over time, and the number for this, the voltage, is 0.199 volts versus the standard hydrogen reference electrode. So if you looked up on your table of reductions, what is the voltage for this reaction? It's going to say 0.199 volts. So that if I'm measuring something relative to that, I need to account for the fact that it's not going to be relative to the hydrogen reference electrode 0, I need to account for the fact that I've got roughly a 0.2 voltage difference between the measurement I'm making on that other side, on my working electrode side, versus the standard hydrogen reference electrode. So our AgCl reference electrode is based on this half reaction where I've got silver chloride picking up an electron to give me silver solid and Cl minus. Right? Remember, this Cl minus is going to be constant in solution, and that's going to be a voltage of about 0.2 volts. It's saturated with potassium chloride at the bottom. Since the chloride concentration is bigger than 1 molar, the potential of the AgCl reference electrode differs slightly from the standard potential. So our E cell for the saturated KCl is a little bit different than 0.22 volts, right? So this 0.22 volts is for this under what conditions? Where this guy is 1 molar. Back in our reference cell, it's not 1 molar because it's a little bit more because we got this down here. It's a saturated KCl solution. So we're going to change that voltage a little bit. So we're going to take our 0.22 volts here, and we're going to adjust it in an inertancy kind of way, where we're looking at the log of the Cl, because this guy's a solid, and this guy's a solid. The only thing that's going to show up is that Cl, and we're going to adjust it by gamma. So we're looking at the activity of the chloride. All right? And when we're doing electrochemistry, looking at activities rather than concentrations is important. Now, obviously, if you've ever picked up a pH meter or something like that, you're not going to just have an AgCl reference electrode sitting there as a beaker with a strip of silver in it and some saturated KCl sitting down at the bottom with the salt bridge. The way they're going to make those is they're going to take that and they're going to repackage it in a coaxial format. It's all along one line. You've got this wire like this. You got your fuzzy AgCl paste, and then down at the bottom you're going to have a little bit of solid KCl and AgCl, and this porous plug is going to serve like the salt bridge does. So in station 3 in our lab, we had a ceramic cup, and that ceramic cup would allow ions to pass through and be exchanged, acting like a salt bridge without actually having a salt bridge. Now that you've got this guy, like I said, it's coaxial. You can package it one within the other, again, kind of like in station 3, where you've got one inside of the other. So this is going to be a double junction Ag reference electrode. We're going to have one and then another, and then you got this other porous plug over here. The repackaged AgCl reference electrode is compact. It's sealed up. Oftentimes there is a little bit of a hole over here, so you can refill it with some electrolyte or solution if you need to. This enables the entire electrode to be dipped into a solution and then analyzed, right? So it makes it sealed up. And the only place we're going to see stuff going is in here, where we've got our porous plug, which is going to allow us to maintain charge neutrality. So this guy is just going to be in one set package, and it's going to hold a voltage of about 0.2 volts, right? Which means that when we read our voltmeter, it's going to take this other solution and its other half cell, which is the iron and the platinum, and it's going to make our measurement relative to that. So just like we did regular old Nernst equations, where we had 2 half cells, boom, we can do that with our reference electrode. The saturated calomel electrode, or SCE, is based on this half reaction where we've got this guy right here is calomel, and it's a mercury chloride. Its potential is going to be 0.268 volts. Right? You've got a saturated KCl solution. Since the concentration of the chloride is bigger than 1 molar, the potential of the saturated calomel electrode is going to be a little bit different than the standard potential. And our equation here is just going to be our E naught for that reaction. And then we're going to do minus the log of the activity of the chloride. Right? Same basic setup. You've got a wire lead coming in here with a platinum wire. You've got some liquid mercury. a mixture of mercury, calomel, and chloride. You have a glass wool down at the bottom, and your saturated KCl is surrounding that. You've got some more KCl, and then you got a porous plug that's going to act like a salt bridge down at the bottom. So you have to contain that. You can't just like stick it in the wire and then the silver chloride is going to stick on the outside of the wire. You've got to give it a little tube to sit in. But again, it's a little bit more stable. Calomel itself is kind of neat. It looks pretty. It's mercury chloride. It's one of those weird things where you're going to form an Hg2Cl2. It's a really common Gen Chem 1 trick question. It was used as a medicine. It caused mercury poisoning very predictably, and they used this for a long time, right? So number 5, calomel tablets there. Comes from the Greek word kalos, meaning beautiful, and melas, meaning black, because it turns black on reaction with ammonia, which was known to alchemists back in the day. Here is a simpler version of that KCl electrode. Its voltage is going to be 0.2444 volts versus the saturated hydrogen reference electrode. Here is the shorthand version. Again, remember, this is just like we're taking one reaction and we're going to say we're going to measure our other reaction on the right-hand side relative to this reference. Right. Chloride is used to maintain a constant ionic strength. You can change this. You've got 0.1 molar KCl solution that is less sensitive to temperature changes, but the saturated KCl is much easier to maintain because maintaining this at 0.1 molar is tricky to do. Right. So real simple, you got a fill hole that you can add to your solution if you need to. You have that calomel in here. You've got some liquid mercury down at the bottom, your saturated KCl solution, and this asbestos fiber that's going to work or porous plug. That'll be a salt bridge. Okay. So how do you convert between the different scales of electrodes? Right? This is important. So if you're looking at your potential, it's going to be the difference between the reduction potential of the indicator and the reference. So versus a saturated hydrogen reference electrode. So let's say I'm measuring something that is versus is 0.22 volts on a saturated calomel electrode. I'm measuring that versus my standard hydrogen reference electrode. I'm going to do 0.22 minus 0. So I'm going to get minus 0.22 volts. If I'm measuring that versus a saturated calomel electrode, and I'm going to do 0.22 minus 0.241 is going to give me minus 0.461. If I'm looking at it versus an AgCl electrode, I'm going to do 0.22 minus 0.197. So I'm going to subtract this little bit off to give me what the true voltage is. All right, so this is what you're reading. That's your indicator, which is what you've read. And then you're going to subtract the reference. So it's going to be read minus ref. Right? So here it is on my saturated hydrogen reference electrode scale. This is my assigned value of my SHE. This is my real value. This is what something is that we've measured. Right? To find out what that is relative to SHE, all we're doing is accounting for what the reference electrode's difference is going to be. So if I'm looking at SHE versus SHE, well, there's no change. If I'm doing it versus an AgCl, well, my reading is going to be offset by 0.241 for the saturated calomel electrode and 0.197 for the AgCl electrode. Right? So it just means you need to account for the fact that your reading is relative to the reference electrode, and unless that reference electrode is the saturated standard hydrogen reference electrode, you're going to need to adjust that voltage a little bit. Not too bad. Right. If the indicator electrode has a potential of plus 0.23 volts versus the saturated hydrogen reference electrode, so this time you're getting a positive reading, you're still going to do the same process. Read the reading minus the reference. So you're going to take your plus 0.2 volts and you're going to subtract 0 if it's a standard hydrogen reference electrode. You're going to take your 0.23 volts and you're just going to subtract 2.41 volts if you're using a calomel electrode. Or you're going to take your reference electrode and you're going to subtract 0.19 volts if it's going to be a saturated silver chloride electrode. Just slight adjustment.